So we're jumping in the middle here of a discussion of repair. We're going to be looking at that today and also tomorrow. What I'd like to do is to just draw your attention to something that many of you have observed, and that is that when I do the antiderivative of some compound function, very often it is the case that when the inside function is linear, then its derivative is constant, and we end up dividing by the constant right here. And that turns out not to be an accident. The reason for it is this. If I do the substitution and I let u equal 5x, then du is equal to 5dx. And I look, and du is sitting right there except for that constant 5. So if this were exactly 5dx right here, then I would integrate the whole form and just get negative cosine 5x. But I don't have it. So what I can do is to introduce that constant by multiplying by 1. Watch this. If I take this antiderivative, and I multiply it by 5 over 5, just like that. Now what I have is the derivative of the outside times the derivative of the inside times an additional constant of 1/5. But because it is constant, I can use the constant multiple rule to pull it to the outside. And what I now have is the antiderivative of sine of u du, which can be integrated instantly to negative cosine of u. And here I did this in kind of slow motion, but you can see all the essential elements. First, I multiplied by 1 to get the constant that I needed. Then I used the constant multiple rule to pull the factor that I didn't need to the outside. And what I was left then was with sine u du, the outside form, which I integrated. So this is repair. And once you get used to it, these steps happen 1, 2, and 3, and it's very, very fast and convenient. Let me show you what I mean by considering the other antiderivative we did in our Quizlet. So, I consider u equals the denominator, 1 minus x cubed. And what is du? You can probably do that in your head. Negative 3x squared. And I look and see that all of du is sitting right there, except for the constant negative 3. So I can multiply this integral by negative 3 and by negative 1/3, which is multiplying by 1 to keep its value. And now I have the form du over u. The integral of du over u is the natural log of the absolute value of u. Boom. We're done. So, we go back to the original integral. This is our original integral right here. And now I'm going to take that integral and I'm going to multiply it by 1. But these constants don't serve the same function. This constant is part of my du. This constant comes to the outside.
And you picked 3.
Because if I let u equal the whole denominator, then du is negative 3x squared dx. Let's do another. Consider first, what is u? What's the obvious choice for u here? 3 plus 2x. Then what is du? 2 dx. It's all right there, except for the factor of 2. So I repair my integral by multiplying on the inside by 2 and on the outside by 1/2. Now here are the two things to check when you repair. The first check is that you should have du, exactly du, sitting right there. The second thing to check is that when I multiply these two constants together, I should get 1, because I'm not changing my integral, I'm keeping the same value. So these are the two things to check when we do repair. Now that I have the du, I'm going to integrate the outside form. So the integral of u to the 5th is 1/6 u to the 6th. But the u that we're talking about is that inside. Now, check. When you check, you give your brain a chance to understand this whole process. So absolutely check all of these, because it really helps you to understand what's going on. There we have the derivative of the outside form times the derivative of the inside. 6 times 2 times 12 is 1, and I get the original integrating back. Does that make sense? Okay. Somewhat. Here? Here to here? Is that what you're asking? Yes, very common question. The 2dx, right here, all of that is du. And this is u to the 5th. So here's one way to think about it. What I'm really doing is taking chain rule backwards. Because the derivative of f of g of x is f prime of g times g prime of x. Therefore, when I integrate this whole form, f prime of g times g prime of x, I get f of g. And that's what I did right here. Here's my f of g, here's my g prime, I get f of g. Better? Okay. Yes, sir.
So we can use just for all linear.
For constant multiples, yeah. Linear is probably too limiting, but linear functions are where it shows up a lot, right? So let me show you one that does not involve a linear inside function. Okay, so we look at this guy and it looks very intimidating, et cetera, et cetera. Definitely not sure what's doing this. So then we start thinking, all right, what could be an inside function? That's an obvious choice for a u here. Negative x squared, exactly so. And so if I let u equal negative x squared, then du would be negative 2x dx. Well, I have all of the components that I need for du except for the negative 2. So I'm going to rewrite by multiplying by negative 2 on the inside and multiplying by negative 1/2 on the outside, repairing my integral. So that now this is in the form of e to the u du, which gives me e to the u plus c. Yes?
Where it is.
Where'd the x go? Okay.
Back to negative 2 is for 3
Okay, so let's be careful here where they came from. I cannot just go throwing pieces into my integral because it makes my life happy. I can only take the original integral that I've got and keep it the same. And I keep it the same by multiplying by 1. So the negative 2 came about, was allowed or justified because I'm really multiplying by negative 2 times negative 1/2, which is 1. See it? So remember our two principles. Number 1, du should be sitting right there. Number 2, the constants should cancel to give me the original value. Because these two have to be equal, otherwise I change my integral. Right? Let's do another. Go for it. Choose u, repair your integral, integrate, check. And if you're playing along at home, you do it too. Pause the video at this time, do the integral, and we'll be right back. Okay, Tony, what you got?
Need the answer.
The process.
I choose 2 minus 7x as u.
Uh-huh.
So du equal to negative 7 dx.
Mm-hmm.
So I put negative 7 in front of dx and negative 1 over 7 outside of 2.
Good.
So I got negative 1 over 7 times 2 over 3.
Mm-hmm.
And times 2 minus 7x to the 3 over 2 plus e. I'm going to check it.
Perfect. And it checked out. That's great. Good job. Anybody have questions on it? Okay. Well, I want to consider now our trig derivatives. We started talking about this on Friday. I want to do this a little bit more. So far, we have, I said derivatives, but it's really antiderivatives that I am concerned about. We have antiderivatives for sine and cosine. What are they? The antiderivative of sine x dx is? Negative cosine x. The antiderivative of cosine? Very good. Now, I'd like to consider the antiderivative of tangent x. By rewriting this as sine over cosine, and since this is a quotient, it makes sense to see whether or not we have a log form. If I let u equal cosine x, then du is negative sine x dx, and that's sitting right there, except with a factor of -1. So I can repair by multiplying on the inside by -1, dividing on the outside by -1. And when I do, I now have the log form du over u, so I immediately get negative natural log of cosine x. This is perfectly fine, but by use of the log property, we can put it into a Spithier form. Like this, and like this. And all of the cool mathematicians write their antiderivative of tangent just like that. Thank you. And the reason for this is that it gives some symmetry. The derivative of tangent is secant squared. The antiderivative of tangent is natural log of secant. And so that helps set things straight. Can you just go over here? So if we want the antiderivative of cotangent, we're going to use much the same plan. We're going to first rewrite as cosine over sine. And then, because this is already in the form du over u, we can integrate directly. We get natural log of the absolute value of sine x. This is, again, a perfectly good answer. But in order to get this to have a form that is parallel here, we're going to actually use a double negative and rewrite this as negative natural log of sine x to the -1 power, or negative natural log of cosecant. Now that might seem like it's unnecessarily complicated, but the idea is to get these two antiderivatives to be parallel to each other. So that again we have derivative of cotangent, negative cosecant squared. Antiderivative of cotangent, negative natural log of cosecant. So it all kind of fits together.
So tangent x is not equal to x.
No, that's the derivative of tangent x. Yes. So students, when they're first learning this, will get it confused a little bit. The derivative of tangent is secant squared, so that the antiderivative of secant squared is tangent. But the antiderivative of tangent is natural log of secant. And you can see this if you take the derivative here. Then you get 1 over secant times the derivative of secant tangent, which gives us tangent. And life is good. Okay. Now, to complete the set, if you've been counting, we have antiderivatives for 1, 2, 3, 4 of our trig functions. I'd like to consider the antiderivatives for the final two, secant and cosecant. And those are going to require a trick. You know this trick. It's multiplying by 1. But the particular form of 1 is very, very tricky. So watch closely. We're going to take this guy, and we're going to multiply by 1 in such a way that we get a log form. The particular choice that we have right here, I would never have come up with on my own. I saw it from somebody. I now pass it along to you. We're going to multiply by secant x plus tangent x divided by secant x plus tangent x. And whoever thought of this should be given a prize.
That's the first thing I think of.
Because it's good for you. Because it is amazingly, amazingly clever, and here's why. Let me simplify. And when I simplify, by distributing at the top there, I get this guy. Now, here's the point. If we consider u equals the denominator, like we frequently have, then du is equal to secant tangent plus secant squared dx. And would you look at that? This right here is du. That right there is u. So I have a very complicated version of the integral of du over u, and I get the natural log of u. Wow. That's pretty wild. Would not have thought of that, but it makes a lot of sense. Let's try cosecant, the antiderivative of cosecant. What do you figure might be a clever thing to multiply by here? That makes a whole lot of sense. Let's try it and see. When I simplify in the numerator, what do I get? And now we consider maybe u equals the denominator, might make sense. So if u is cosecant plus cotangent, then du will be negative cosecant x cotangent x minus cosecant squared x. All of that is dx. This is the opposite of that. Okay. So I can repair with a minus 1. And when I do, I get negative integral of du over u, which is the negative log form. Just like this. Now, this is a perfectly good answer. Some textbooks will write it in a slightly different form. So let me show you the alternate form for this. I have seen this on the AP exams. If I use this as an exponent, the usual log trick, then I can write this as the natural log of cosecant plus cotangent to the minus 1. Now, we can rationalize by multiplying top and bottom by cosecant minus cotangent. And when we do, in the denominator, something wonderful happens. And that is that I get cosecant squared minus cotangent squared. But if you remember your trig identities, cosecant squared is equal to cotangent squared plus 1. So that cosecant squared minus cotangent squared is simply 1. And this whole thing collapses to a pretty convenient form, cosecant minus cotangent. When you look at the algebra involved here, if I take this and set it equal to that, it looks as if I did something that was completely algebraically wrong. It looks as if I took this negative sign and just arbitrarily moved it to the inside on one term. That's not what I did. What I did was actually to use that as an exponent and rationalize and get this out. So you'll see both of these forms in the textbook, but I like the one in green right here because it has a nice parallel to the invertible secant, which is natural logothetical standard.
So we know.
No, you don't have to. These are alternate acceptable forms. Yep. Okay, how are we doing? Tonight's homework, we'll have you practicing this, and then we'll do some